Hello, Maurits here. Now I will talk about the circular motion of charges in a magnetic field. Okay. Say we have some kind of magnetic field, say it's directed outwards here, and say we have a positive charge coming in from this direction with a velocity v. Then we know from earlier on that we have a law for this. The force from a magnetic field on a moving charge is q vb times sine of the angle, but this is perpendicular to the field, so it will just be this. And say this is a positive charge, then the current is going that direction. The field is pointing upwards, and that means that we have a force pointing in that direction. So the particles start to move in a curve like this, but the force will still be pointing always perpendicular, and that will mean that this will in the end turn into a circular path if the magnetic field is big enough. So we are having a situation where we have a circular motion with some kind of force pointing inward. Oh, wait a minute, that is exactly what we talked about the last section about centripetal force, and there we found that the force centripetal is mass times a velocity square over the radius. Let's use capital R here. And our goal is now to find the radius of this orbit. That is the first goal. Okay, so what can we do here? Of course, this centripetal force is supplied by the magnetic force there. These two are the same. That magnetic force is what causes this centripetal force. They are, a centripetal force is always caused by something. In this case, it's caused by the magnetic field. So that means that we can put these to become equal. So QVB must be mv square over r. We can cancel away v there, one of them. We can then multiply by r and divide by b and divide by q, right? To get that r equals to m v that we're left there divided by the qb. So there we have a formula that will give us the radius of a circular path for an electron moving in or some charge moving in a magnetic field. Say, for example, we can take an electron. The mass of an electron is about 9.11 times 10 to the power of minus 31 kilograms. The charge of an electron, I say E here, but actually negative E, but we only care about the radius of this path, is 1.60 times 10 to the power of minus 19 columns, right? And say we have a velocity that is very high, but not so high for an electron. Say 1.6 times 10 to the power of 7 meters per second. And our goal, and we have a magnetic field strength of the Earth by field, so about 550 micro Tesla close to the Earth. And that will give us a radius of mv over qb, so 9.11 times 10 to the power of negative 31 times why did I want write 1.6 1.0 actually takes 0 So we can have three significant figures in the end, so 1.00 and 50.0 there. Times 1 times 10, so 1 times 10 to the power of 7 here, right? Divided by charge, that is 1.6 times 10 to the power of minus 19 times B, that is 50 times 10 to the power of minus 6. So, calculator, why did I hide away that? I will take our calculator and we do a little bit of calculation. Actually, I've done this already. So we can do the calculation here. Okay, 9.11 e minus 31, right, times 1 e7 divided by bracket 1.6 e minus 19 times 50 e minus 6 in bracket x, and we find an radius about 1.14 meters. This is, by the way, basically what happens with electrons moving in the Earth magnetic field. If you have the Earth and the magnetic field around it, somewhat like this, right? And we have a charge coming in from the sun, say it comes in at a little bit of angle here, this is the field, then it will experience a force that makes it go, since it's tilted towards, it will change only its radial component, and it will go in an orbit like this, and as the field lines get closer and closer, it will go tighter and tighter down here, and actually if one do the geometry on this, one can see that it will spiral out, and then it will spiral down on the other side and back and forth from pole to pole. And this will actually dive a bit into the atmosphere and going out again. And as it dives down, sometimes it interacts with atoms, ionizing them, and they will give off radiation. And that is what we have, northern, of course, northern and southern light. Electrons and protons coming in from the sun will bounce back and forth, rotating, spinning around in the magnetic field like this. That is rather cool. Okay. Next thing we will look at here is what will the time be, the period of this motion. Okay, so we know of course that the velocity of something is the distance over time. For an orbital motion, that will be the distance would be 2 pi r, right? And the time would be the period for one turn. So that means that we can write that the period is 2 pi r over v, right? Or 2 pi divided by v times r. Now we can take this r from that formula, pull it over there, right? So t equals to 2 pi over v times mv over qb. You can cancel something here, right? Yeah, cancel away the velocity and we end up with this formula. 2 pi m over qb. That will be our period. And an interesting fact of that is that the velocity is cancelled away. The velocity of the particle does not matter. And the radius doesn't matter either, because that's dependent on the velocity. So only the mass, what charge you have, and what strength of the magnetic field will matter. And this is used in a kind of accelerator, particle accelerator, called cyclotron. Was used. Actually, it is still used, but not as much as before. And it's particular, in a sense, it's actually used more, because I think the microwave, there is cyclotrons basically in microwaves. Okay, so what we have here is, what we will do is basically we'll take two halves. Think about a very thin can, and you split it into two halves. This is seen from above. Seen from the side, it's like we cut it up like this, are two half moons with a little gap in between. We put that in a uniform magnetic field. Say the field is pointing inwards here. And uniform means that it has the same strength all over in the same direction. And inside here we have a little, say, electron gun that sends out an electron that will start to move in a circular path. And as this is going on, we will charge this end, this half of this cyclotron, these two shells. They are conducting, and we'll charge that as a negative and this as positive. So it will be repelled by this and attracted by that. So over this little gap between the two halves, it will accelerate. And then on this side, it will start to move in a curve again. And as it moves over here, we will switch the polarity of these two. Now it will repel by this and attract by that, accelerating over the gap. High speed, it will go out in a larger and larger orbit, and that will take the same time. That means that we could feed this with AC voltage with the frequency fitting this. So this will spin, and the orbit will get higher and higher and higher. And in the end, you will have some kind of opening. Let's say this half stretches out a little bit more than the other half, like that. So you make a gap here. So as it traverses around here, sooner or later it will hit this gap and come out with a high speed. All of this is in vacuum, by the way. So here you could have now a tunnel evacuated tube, and here you have some kind of target, and that will be a kind of accelerator that's built on that. The speed of the particle doesn't matter, the period will be the same anyhow. Okay, thanks.